All right, welcome to Dynamics. Today we're going to be continuing in chapter 13 with going into the NT system and doing what we did last time, which was using Newton's second law to say force equals mass times acceleration, where we split it last time into the sum of the x forces on the left side of the equation, the statics force side, right, equals the mass times acceleration in the x, where we could do the sum of the force in the y equals may, right? And now we'll do it with the n and the t. Same idea, sum of the forces in the n equals the mass times acceleration in the n, or same thing for the t, right? And so we need to just review a little bit of that from chapter 12, but then we'll just be doing some applications in the NT coordinate system. So anytime we've got something with a radius that we can identify, um, we can pretty easily make our particle then be going around some curve with a tangential coordinate and a normal coordinate going inward to the curve, right? So something like this would definitely work for that. We could come up with the acceleration tangentially and normally inward to the curve. So let's see if we can remember what those were. The normal component, MAN, right? We could do the same thing as last week and say the sum of the forces in the N. That would be called well, yeah, that would be the centripetal force trying to push it outwards, right? You could also have the uh, positive in direction, excuse me, centripetal would be the inward, right? Like your friction if you're going around a curve in a car or something like that. It would be opposite of centrifugal. The positive in direction then is always which direction? Normal to the tangential component. Well, that's true. They're perpendicular. It's always directed towards the center of curvature. That was true, right? We always wanted it to be inward on the curve so that it was always a positive a sub n. It's normal to the binormal component. We haven't talked about that really, but that would be the third axis that is perpendicular to both the n and the t. And yep, that's also true. So that would be D, all of the above for that guy. And we'll talk more about that binormal. It would be like the z-axis that sticks up perpendicular to both the n and the t. Here's another example of something that we could actually calculate today. We could calculate what's the needed friction or what's the necessary banking angle if we don't want to depend on friction to keep the cars from sliding out of the circle, right? We could come up with that centripetal force needed to direct it inward and keep it from sliding. Or we could say what's the maximum velocity given a certain radius, all those different things to keep them from sliding. So a lot of good traffic applications for sure. And we've got to have an amusement park application. Excuse me. It's a Monday, so the amusement park going in a circle, we've definitely got some fixed radius things that we could call a mass going around a fixed radius. Classic NT situation where we could apply what we're learning today. And if we knew what that acceleration was, we could say, okay, well, what's the force pulling on that big arm? And we could design the structure to resist that. Okay. Oh, that's an interesting question as well. If we knew the mass of someone in those, what's the smallest angular velocity of that thing spinning around so that someone barely stays in contact with their seat, right? They feel weightless, but they don't fall and hit their head on the top side of the trolley piece that they're sitting in. So kind of interesting. Here's one last one. You could have something with a circular or maybe elliptical orbit that we could come up with a normal and a tangential acceleration, right? And that would be an interesting problem, right? We could determine what's the right speed to maintain a certain distance from the Earth, right? If we wanted it to be a certain radius as it's orbiting, what would its speed need to be? So a lot of good applications now that we're not only finding the accelerations, but we're using that acceleration to determine what sort of force, or maybe, we know what force we need, and we need to find the radius, something like that. But combining that using Newton's second law is going to allow us to do a lot more types of problems with the normal tangent coordinate system. So just to remind ourselves, we had a tangential component of our coordinates, and that was tangent to the path. So that was 100% of our velocity. And then normal to that, we had inward to the curve was positive, the normal coordinate. Now we'll add in this binormal. Oh, and there's what we talked about before. Now we'll add this binormal axis here, which is perpendicular to both of those. So like we talked about, yeah, there's the in going inward on the curve, tangent in the direction of the velocity. Now we had this MAT and MAN. Now, if we wanted to do our statics on the left side and our dynamics on the right side, right, we can make even a free body diagram and have that picture on the left. And we can make a kinetic diagram and have that on the right with MAT or MAN. And that's where we'll be going with it. And since we're following that particle as it goes around a curve wherever it goes, right? That's going to make the axis that's perpendicular to both of those always be non-accelerant, right? It's not going to be accelerating in the binormal direction. And so that's always going to end up just being zero. So putting it all together with our review, we had AT was just the time derivative of the velocity. And then the normal component of acceleration was v squared over rho, where rho was the instantaneous radius of curvature. Sometimes there's a constant radius. If we needed it to be instantaneous for some function, right, then we could do dy dx a couple of times and solve for an instantaneous rho, even if it's not a constant radius. All right, so there's our review, and we will give it a shot here with some examples now.